Welcome to the basics of fluid mechanics. What is fluid mechanics? Fluid mechanics deals with the study of all fluids under static and dynamic situations. Static means at rest and dynamics means in motion. Fluid mechanics studies the forces acting on fluids at rest and in motion. It has got a wide range of applications in engineering. Some of the applications are automobiles. You can see the air flowing over the car. This air causes a drag force in the car. The car is designed in such a way that the drag force is reduced. Also in sports car, the spoiler is attached to the rear end of the car to counter the lift force generated by the air. The spoiler is designed using the principles of fluid mechanics. Fluid mechanics has got a lot of applications in heat engines. In heat engines, the air, which is a fluid, is the working medium. The dynamics of air is studied to design the combustion chamber and also to improve the efficiency. In hydroelectric power plants, the water, which is a fluid, flows through the turbine to generate power. An engineer needs to use the basics of fluid mechanics to calculate the power developed by the turbine and also to design the whole plant. The wind turbines are designed using fluid mechanics principles to generate maximum power. The blades of the turbine are designed aerodynamically to improve the efficiency of the turbine. What exactly is a fluid? A substance usually exists in three phases, that is solid, liquid and gas. Both liquid and gas come under the category of a fluid. What is the difference between a solid and a liquid? It is solely based on its ability to resist an applied shear stress. In this video, you can see the solid stops deforming after a limit, but the liquid deforms continuously upon the action of a shear stress. What is shear stress? Shear stress is the stress that causes the material to shear. How a solid deforms upon a shear stress? You can see a solid placed between two plates. The solid is fixed between two plates. When a tangential force is applied, a shear stress acts on the solid at the top. The shear stress is equal to the tangential force by the surface area. An equal and opposite shear stress is developed at the bottom to counter the shear stress at the top. This causes the solid body to deform. If the shear stress is within the elastic limit, the solid stops deforming, and when the shear stress is removed, it returns to its initial position. The shear stress causes a shear strain, which is defined as delta x by delta y, which is equal to tan theta. And since theta is small, tan theta can be approximated as theta. If a fluid element is kept between two plates when a shear stress is applied, just like the earlier case, the fluid will deform continuously without offering any resistance. So, the definition of a fluid is that any substance which deforms continuously upon the action of a shear stress, however small it is. In the case of a fluid, instead of shear strain, we take the shear strain rate because the plate is moving continuously without any resistance. So shear strain rate is equal to d by dt of tan beta, and tan beta is equal to delta x by delta y. So shear strain rate is equal to tan beta dot, that is equal to d by dt of delta x by delta y. And tan beta dot is equal to delta u by delta y, because d by dt of delta x is equal to delta u. And when the limits are applied, tan beta dot is equal to du by dy. In solids, shear stress is proportional to strain. That is, tau is directly proportional to tan theta. In fluids, shear stress is proportional to strain rate. That is, tau is directly proportional to tan theta dot. So what is continuum? Matter is made up of atoms that are widely spaced in the gas phase. Yet, It is very convenient to disregard the atomic nature of a substance and view it as a continuous homogeneous matter with no holes, that is continuum. The continuum idealization allows us to treat properties as point functions and to assume that the properties vary continually in space with no jump discontinuities. Here you can see the left side figure, that is a continuum idealization, and the right side you can see the rarefied gas. You can see the difference that in the continuum idealization, the distance between the atoms can be almost neglected. And in the rarefied gas, the distance between the molecules is significantly high. So how do you make a classification between continuum and rarefied gas? The continuum model is applicable as long as the mean free path is much lower than the characteristic length. Mean free path is the distance traveled by the molecules between two successive collisions. You can see here one molecule here and another here. So the distance traveled by the molecule between two successive collisions is called mean free path, that is lambda. And the characteristic dimension here is L. It can be either length or breadth, which will be of comparable value. When lambda is very large compared to the characteristic length, gas will become rarefied. A simple dimensionless number is used to distinguish between continuum model and rarefied gas model, and the dimensionless number is called Knudsen number. See, the Knudsen number is defined as the ratio of mean free path by the characteristic length. So if Knudsen number is less than 0.01, then you can make the continuum idealization. And if the Knudsen number is more than 0.01, rarefied approach should be made. Here lambda is the mean free path and L is the characteristic length. That can be either breadth, you can take breadth, length or diameter. So what is a rarefied gas? In a rarefied gas, Knudsen number will be greater than 0.01. Okay, you can see in this rarefied gas model, see lambda is of comparable value as that of L. So if lambda by L is greater than 0.01, continuum idealization cannot be taken and rarefied gas approach need to be taken. So what are the various physical properties of fluids? Some of the important physical properties of fluids are density, specific weight, vapor pressure, and viscosity. There are other physical properties, but let us discuss the first four properties in detail. So what is density of a fluid? Density of a fluid is defined as mass by volume. That is M by V. So density of water is commonly used fluid is 1000 kilogram per meter cube. And what is specific volume? That is the volume of the fluid divided by mass. That is the reciprocal of density. that is equal to 1 by rho. Nu is equal to 1 by rho. So what is specific gravity or relative density? Here we are making a comparison with respect to the density of water. So specific gravity is defined as density of the fluid divided by density of water. That is called specific gravity. So what is specific weight? Specific weight is defined as density of the fluid into acceleration due to gravity. So that is specific weight. So what is vapor pressure and what is cavitation? Both are related to each other. So let us understand what is vapor pressure first. The pressure exerted by its vapor in phase equilibrium with its liquid at a given temperature is called vapor pressure. So you can see in the figure, so there is evaporation taking place. We will discuss about evaporation in detail. So the pressure exerted by this vapor is called vapor pressure. So what is evaporation? Evaporation is a surface phenomenon in which liquid at the surface is converted to vapor. You can see that here. The liquid is getting converted to vapor. The atmosphere exerts a pressure downward, which is equal to the sum of partial pressures of water vapor and dry air. At surface, some vapor is converted to liquid, and at equilibrium, amount of liquid getting converted to vapor is equal to the amount of vapor getting converted to liquid. You can see liquid is getting converted to vapor here, and also some of the vapor will get converted to liquid. So at equilibrium, the amount of water getting converted to vapor will be equal to amount of vapor getting converted to liquid. So both will be equal. That is called an equilibrium. At this point, the pressure exerted by the vapor is called vapor pressure. See, on the top of this beaker there will be an atmosphere. There will be water vapor and also other gases, vapors of other gases, that is oxygen plus nitrogen. The water will be of very small amount. So partial pressure is defined as the pressure of gas or vapor in a mixture with other gases. Okay, so if you take atmosphere, you can see that there will be water vapor, that is of blue color. There will be water vapor and also oxygen molecules, nitrogen molecules, etc. So this atmosphere will exert a pressure downward, which causes some of the vapor to enter into the liquid, getting converted to liquid. So the partial pressure is defined as the pressure of a gas or vapor in a mixture with other gases. You can see this in the atmosphere, there will be water molecules, and these water molecules, the pressure of these water molecules is defined as the partial pressure of water vapor in atmosphere. So let us take an example, that is evaporation of water at 20 degrees Celsius. You can see in the figure, the vapor pressure of water at 20 degrees Celsius is 2.34 kilopascal. And the partial pressure of water vapor is 0.34 kilopascal. Therefore, a bucket of water at 20 degrees Celsius left in a room with dry air at 1 atmosphere will continue evaporating until one of the two things happen. The water evaporates away, that is, there is not enough water to establish phase equilibrium in the room, or Evaporation stops when the partial pressure of water vapor in the room rises to 2.34 kilopascal, at which point phase equilibrium is established. So you can see in the figure 1 there is evaporation taking place, and in figure 2 you can see that some of the vapor is getting converted to liquid, that is entering into the liquid surface. And in the figure 3 you can see that the phase equilibrium is established, that is vapor pressure will become equal to the partial pressure. That is, so some of the water vapor in the atmosphere is entering into the liquid surface. So amount of liquid getting converted to vapor will be equal to the amount of vapor getting converted to liquid. This happens when the vapor pressure is equal to the partial pressure. So in figure 3, when the phase equilibrium is established, vapor pressure is equal to 2.34 kilopascal and partial pressure is equal to 2.34 kilopascal. In the left hand you can see that in figure 1 the vapor pressure is equal to 2.34 kilopascal and partial pressure is equal to 0.34 kilopascal. In figure 1 there is no phase equilibrium, and in figure 3 there is phase equilibrium. So what is the difference between boiling and evaporation? Both boiling and evaporation, liquid is getting converted to vapor. See, in evaporation, it is a surface phenomenon, whereas in boiling, vapor bubbles form from the bottom. You can see the vapor bubbles here. It forms from the bottom. Boiling occurs when the vapor pressure is greater than atmospheric pressure. This can occur in two ways, either by heating the liquid or by reducing the atmospheric pressure. So we have seen that there is an atmosphere pressure acting on the top of the liquid. So when the vapor pressure is more than the atmospheric pressure, boiling can occur. But evaporation, it is a surface phenomenon. It occurs continuously. So that means there is some liquid getting converted to vapor and some vapor converted to liquid. And the pressure exerted by this vapor is called vapor pressure. We have seen that earlier. And in evaporation, bubbles cannot form since the vapor pressure is less than the atmospheric pressure. So what is cavitation? So once you have understood what is vapor pressure, what is evaporation, and what is boiling, let us see what is cavitation. Cavitation is one of the important things you need to know in fluid mechanics. Cavitation is defined as the process of formation of vapor phase of a liquid when it is subjected to reduced pressures at ambient temperature. So we have seen that water boils when the vapor pressure is greater than the atmospheric pressure. Okay, so that means that can happen in two ways, that is either by supplying heat, heating the liquid, or by reducing the atmospheric temperature or reducing the atmospheric pressure. So you can see that in this figure there is a pressure drop in the middle, that is called the throat region. So when the pressure is dropped, that means when the pressure is low, pressure is lower than the vapor pressure, boiling occurs. So it is not by heating the liquid but by reducing the pressure. So here the pressure, that is the pressure is taken as the atmospheric pressure. So when the pressure is very low, boiling occurs. And this vapor bubbles get travel to the other regions. You can see that is called cavitation bubbles, and these bubbles expand and these bubbles later collapse, releasing intense energy, and this can harm some of the equipments. So cavitation is defined as the process of boiling in liquid as a result of pressure reduction rather than heat addition. So that is very important because here water boils due to pressure reduction rather than heat addition. So you can see that here the cavitation bubbles. The vapor bubbles called cavitation bubbles, since they form cavities in the liquid, collapse as they are swept away from the low pressure regions, generating highly destructive, extremely high pressure waves. You can see that in the figure, the bubbles continuously expand and finally it collapses, releasing huge energy which can harm the equipments, particularly hydraulic machineries. So, for example, water at 10 degrees Celsius will flash into vapor and foam bubbles at locations. That is, water at 10 degrees Celsius will flash into vapor and foam bubbles at locations such as the tip regions of impellers or section side of pump, where the pressure drops below 1.23 kilopascal. So you can see that because of cavitation, the impellers are getting damaged. Here the water is boiling at 10 degrees Celsius because of the pressure reduction. Because the pressure here gets dropped to 1.23 kilopascal, which is much less than the vapor pressure at 20 degrees Celsius. Hence the water boils and form cavitation bubbles, and these cavitation bubbles, when they burst, release a huge energy which can damage the impellers. So you can see in pumps at the section side the pressure will be very low. So here the pressure will be very low. Here you can see that cavitation bubbles form, and these bubbles, when they burst, can damage the impellers, just like we have seen in the earlier slide. So what is viscosity? So viscosity is defined as the internal resistance of a fluid. It is a common knowledge that different fluids flow differently. This is due to the viscosity of different fluids. You can see in the figure how a honey flows and how water flows. Water almost flows without any resistance, but in honey it flows with some kind of a resistance. So what is a difference between a solid and a liquid? We have discussed it earlier, but let us discuss it again. So you can see in solid, when a force is applied, a shear stress develops and it stops deforming after a limit. In liquid, when a force is applied, when a tangential force is applied, it will deform continuously without any resistance. That is the definition of a fluid. So you can see here tan beta can be approximated as beta, since the angle is very low, and tan beta is equal to delta x by delta y. So tan beta is equal to delta x by delta y, and when the limits are taken, beta can be taken as dx by dy. So in fluids, we are not taking shear strain, we are taking shear strain rate, that is beta dot, shear strain rate. So that is equal to d by dt of dx by dy. So that is equal to du by dy. So that is very important. In solid, we take beta, that is shear strain, and in liquid, we take beta dot, that is equal to du by dy. So what is Newton's law of viscosity? So we have seen in liquids, when tangential force is applied, it will deform continuously. So a shear stress is developed at the top and an equal and opposite shear stress is developed at the bottom to counter the shear stress at the top. So the shear stress is equal to force divided by area. That is tangential force divided by the surface area. And the shear stress we have seen in liquids, shear stress is directly proportional to shear strain rate. So that is how Newtonian fluids are discussed. Newton's law of viscosity states that shear stress developed is directly proportional to shear strain rate, that is beta dot. So those fluids which obey Newton's law of viscosity are called Newtonian fluids. That means in those liquids where shear stress is directly proportional to shear strain rate, they are called Newtonian fluids. So that means tau is equal to du by dy. We have seen that beta dot or shear strain rate is equal to du by dy. It is the velocity gradient. U is the velocity gradient. So tau is equal to mu into du by dy, and this mu is called viscosity. The constant of proportionality is called coefficient of viscosity or dynamic viscosity. We call mu as dynamic viscosity. This is called dynamic viscosity. So what is the unit of viscosity? So you know that tau is equal to mu into du by dy. So mu is equal to tau divided by du by dy. So let us take the dimensions here. So the dimension of shear stress is dimension of stress, that is Newton by meter square, and the dimension of du, that is velocity, is meter per second, and dy the dimension is meter. So that is Newton second by meter square. So the unit of viscosity in SI unit is Newton second by meter square. So what is this unit in CGS unit? The unit is poise in CGS unit, and 1 Newton second by meter square is equal to 10 poise. So what is kinematic viscosity? Kinematic viscosity is defined as dynamic viscosity by density. That is nu is equal to mu by rho. So what is the unit of kinematic viscosity? Kinematic viscosity, so we have seen that the unit of mu is Newton second by meter square, and rho, you know, density, that is mass by volume, that is kilogram by meter cube. So that is equal to Newton meter second by kilogram. So the Newton, if you write the units, you can get it as kilogram meter by second square, because Newton, that is force, is equal to mass into acceleration. The unit of mass is kilogram, unit of acceleration is meter per second square. So if you simplify it, you will get meter square by second. So unit of kinematic viscosity is meter square by second, and the unit is meter square by second in SI unit, and in CGS unit the unit is stoke, and 1 stoke is equal to 10 raised to minus 4 meter square by second. So what is the effect of temperature on the viscosity of a liquid? You can see here the viscosity in liquid is due to the intermolecular forces. So as the temperature increases, the intermolecular forces will get reduced. So that means the viscosity will also get reduced in case of liquid, because viscosity is due to the intermolecular forces. So as intermolecular forces are reduced, viscosity will also get reduced. So what is the effect of temperature on the viscosity of gas? So unlike liquids, the viscosity of gas is due to intermolecular collisions. So here the intermolecular forces are comparatively very weak, and viscosity is due to the intermolecular collisions. So as the temperature increases, the intermolecular collisions will increase. So the viscosity is due to the intermolecular collisions. So the viscosity will increase. So what is viscosity? So viscosity is defined as the internal resistance of a fluid. It is a common knowledge that different fluids flow differently. This is due to the viscosity of different fluids. You can see in the figure how a honey flows and how water flows. Water almost flows without any resistance, but in honey it flows with some kind of a resistance. So what is a difference between a solid and a liquid? We have discussed it earlier, but let us discuss it again. So you can see in solid, when a force is applied, a shear stress develops and it stops deforming after a limit. In liquid, when a force is applied, when a tangential force is applied, it will deform continuously without any resistance. That is the definition of a fluid. So you can see here tan beta can be approximated as beta since the angle is very low, and tan beta is equal to delta x by delta y. So tan beta is equal to delta x by delta y, and when the limits are taken, beta can be taken as dx by dy. So in fluids, we are not taking shear strain, we are taking shear strain rate, that is beta dot, shear strain rate. So that is equal to d by dt of dx by dy. So that is equal to du by dy. So that is very important. In solid, we take beta, that is shear strain, and in liquid we take beta dot, that is equal to du by dy. So what is Newton's law of viscosity? So we have seen in liquids, when a tangential force is applied, it will deform continuously. So a shear stress is developed at the top and an equal and opposite shear stress is developed at the bottom to counter the shear stress at the top. So the shear stress is equal to force divided by area, that is tangential force divided by the surface area. And the shear stress we have seen in liquids, shear stress is directly proportional to shear strain rate. So that is how Newtonian fluids are discussed. Newton's law of viscosity states that shear stress developed is directly proportional to shear strain rate, that is beta dot. So those fluids which obey Newton's law of viscosity are called Newtonian fluids. That means in those liquids where shear stress is directly proportional to shear strain rate, they are called Newtonian fluids. So that means tau is equal to du by dy. We have seen that beta dot or shear strain rate is equal to du by dy. It is the velocity gradient. U is the velocity gradient. So tau is equal to mu into du by dy, and this mu is called viscosity. The constant of proportionality is called coefficient of viscosity or dynamic viscosity. We call mu as dynamic viscosity. This is called dynamic viscosity. So what is the unit of viscosity? So you know that tau is equal to mu into du by dy. So mu is equal to tau divided by du by dy. So let us take the dimensions here. So the dimension of shear stress is dimension of stress, that is Newton by meter square, and the dimension of du, that is velocity, is meter per second, and dy, the dimension is meter, so that is Newton second by meter square. So the unit of viscosity in SI unit is Newton second by meter square. So what is its unit in CGS unit? The unit is poise in CGS unit, and 1 Newton second by meter square is equal to 10 poise. So what is kinematic viscosity? Kinematic viscosity is defined as dynamic viscosity by density. That is, nu is equal to mu by rho. So what is the unit of kinematic viscosity? Kinematic viscosity, so we have seen that the unit of mu is Newton second by meter square, and rho, you know, density, that is mass by volume, that is kilogram by meter cube. So that is equal to Newton meter second by kilogram. So the Newton, if you write the units, you can get it as kilogram meter by second square, because Newton, that is force, is equal to mass into acceleration. The unit of mass is kilogram, unit of acceleration is meter per second square. So if you simplify it, you will get meter square by second. So unit of kinematic viscosity is meter square by second, and the unit is meter square by second in SI unit, and in CGS unit the unit is stoke, and 1 stoke is equal to 10 raised to minus 4 meter square by second. So what is the effect of temperature on the viscosity of a liquid? You can see here the viscosity in liquid is due to the intermolecular forces. So as the temperature increases, the intermolecular forces will get reduced. So that means the viscosity will also get reduced in case of liquid, because viscosity is due to the intermolecular forces. So as intermolecular forces are reduced, viscosity will also get reduced. So what is the effect of temperature on the viscosity of gas? So unlike liquids, the viscosity of gas is due to intermolecular collisions. So here the intermolecular forces are comparatively very weak, and viscosity is due to the intermolecular collisions. So as the temperature increases, the intermolecular collisions will increase. So the viscosity is due to the intermolecular collisions. So the viscosity will increase. In this lecture, we will do a problem on viscosity. The problem is an infinite plate is moved over a second plate on a layer of fluid. For a small gap width, that is d is equal to 0.3 millimeter. We assume a linear velocity distribution in the liquid. The liquid velocity is 0.065 Newton second per meter square and its specific gravity is 0.9. Lower plate is fixed and the upper plate is moving with a velocity of 0.3 meter per second. Determine first the kinematic viscosity of the liquid, shear stress on the upper plate in Newton per meter square, the shear stress on the lower plate in Pascal, the direction of each shear stress calculated in parts B and C. So you can see this plate A and plate B here, and the distance between these plates is given as 0.3 millimeter, and the lower portion the velocity is equal to 0, and the upper portion plates moves at a velocity of capital U, that is given as 0.3 meter per second. And the liquid viscosity is given as mu is equal to 0.065 Newton second per meter square, and the specific gravity of the oil is zero point 0.9, and the lower plate is fixed and the upper plate is moving with the velocity 0.3 meter per second. First you need to find the kinematic viscosity of the oil. So the kinematic viscosity of the oil, nu, is given as mu by rho, the dynamic viscosity by density. That is the formula for that. So the dynamic viscosity is given by 0.065 Newton second per meter square divided by, so the density here is 900 because the specific gravity is given as 0.9 and density is specific gravity into 1000, that is 900. 7.22 into 10 raised to minus 5 meter square per second. So how will you find the shear stress on the upper plate? So according to Newton's law of viscosity, you know tau is equal to mu into du by dy. Since it has got a linear velocity profile, you can write mu into delta u by delta y, that is equal to mu is equal to 0.065 into delta u, that is the difference between velocity between the lower plate and the upper plate. So the lower plate velocity is 0 and the upper plate is moving with the velocity 0.3 meter per second. So that is equal to 0.3 minus 0 divided by delta u is the thickness of the film, that is equal to 0.3 millimeter. 0.3 into 10 raised to minus 3. So that is equal to 65 Newton per meter square. So you can see that, see, in the lower portion of the plate, shear stress will be in this direction, will be in the opposite direction, and the upper portion shear stress will be in this direction, and this both, the magnitude of both the shear stress will be equal. So this is the shear stress in the lower plate and this is the shear stress in the upper plate. The directions are opposite. In this lecture, we will see what are the different types of fluid. The first classification is between the ideal and real fluid. So, what is an ideal fluid? Ideal fluid is a fluid which has got zero viscosity and also it is incompressible. That means its density will not change. A real fluid is a fluid which has got non-zero viscosity and also it is compressible. There is a difference between an ideal fluid and a real fluid. Now let us see different types of fluids. See, we have already discussed Newton's law of viscosity. So the fluids which obey Newton's law of viscosity is called Newtonian fluid. And fluids which does not obey Newton's law of viscosity is called non-Newtonian fluid. So what are the various non-Newtonian fluids? You can see some of the fluids here. First one is a dilatant fluid. This is called a shear thickening fluid. In this figure you can see that shear stress tau is in the y-axis and shear rate K is in the x-axis. So Newton's law of viscosity states that tau is equal to mu into du by dy. That is, du by dy is the shear strain rate, that is K here, and tau is the shear stress. So for a Newtonian fluid, viscosity mu, that is the slope here, it will remain unchanged. So viscosity will not vary. But take the case of a dilatant fluid. In a dilated fluid, when the shear stress is increased, you can see that, the viscosity increases. As the shear rate is increased, you can see the slope is continuously changing. So that means viscosity increases continuously. So that is why it is called a shear thickening fluid. So one example is the quicksand. Now look at another fluid, that is pseudoplastic fluid or shear thinning fluid. That means when you apply the shear stress, shear strain rate increases. You can see here the slope is decreasing. That means viscosity is getting reduced as shear rate is increased, as strain rate is increased. These are called pseudoplastic fluid, and example include blood. For Newtonian fluids, some examples are water and glycerin. Honey is also a type of Newtonian fluid. And then you have a Bingham plastic fluid. You can see that it will obey just like a solid up to a limit. After that, it will behave as a Newtonian fluid. Examples are muddy water or sludge. It needs an initial push. After that only it will undergo deformation. So these are the important types of fluid other than Newtonian fluids. For most cases we will studying here only about Newtonian fluids. There is another branch of study called rheology to deal with other types of fluid. For that means fluids which has got varying viscosity.
The dynamic viscosity of oil used for lubrication between a shaft, there is a journal, and a bearing is 6 poise. The shaft is of diameter 400 mm and rotates at 190 rpm. Calculate the power lost in the bearing for 90 mm long journal bearing arrangement. Thickness of the oil is 1.5 mm. So you need to find the power lost in the bearing. So the power is lost because of the friction due to the liquid. So this journal is rotating in this bearing. So since it has to overcome the friction due to the oil, that is due to the viscosity of the oil, you need to find out the power lost. So first you need to understand that you need to know the Newton's law of viscosity, that is tau is equal to mu into du by dy. Because of this viscosity, a shear stress is created between the journal and the bearing. You know that the journal is rotating, that means it will have a linear velocity at this end. So it will be like this. So if I draw it here, it will appear like this. So this is the velocity variation. So this is the velocity of the journal. At this end, the bearing end, the velocity will be 0. So delta U will be equal to V minus 0, and this is the thickness of the oil film. So delta Y is equal to T minus 0. So that is T. And du by dy can be approximated as delta U by delta Y, since it has got a linear velocity profile. Here it is not given, but you can assume it to be a linear velocity profile. So what is velocity V of the journal? That is the linear velocity of the journal. That is equal to angular velocity into radius. That is equal to omega into d by 2. Radius is the diameter by 2. And omega is equal to 2 pi n by 60. So velocity will be equal to 2 pi n by 60 into we can write capital D by 2, that is equal to pi dn by 60. If you solve that, you will get velocity to be 3.97 meter per second. So what will be the shear stress? Shear stress will be equal to mu into delta U by delta Y. So that is equal to mu, it is given, the dynamic viscosity is given as 6 poise. So if you convert to SI unit, it is 0.6 Newton second per meter square into delta U by delta Y. So that is equal to 3.97 minus 0 by 1.5 into 10 raised to minus 3. So if you solve that, you will get 2646.67 Newton per meter square. So what will be the force? Force is equal to this shear stress will be acting here like this at the end. So force is equal to tau into area, that is tau into area is equal to pi into d into L. L is the length of the shaft. So you will get 2646.67 into pi into diameter here is equal to 400 millimeter. So it is 0.4 and length is 90 millimeter, that is 0.09. So you will get the force as 299.33 Newton. So this is the opposing force. So what is the power lost? So power lost is equal to force into velocity, that is linear velocity, that is 299.33 into 3.97, so that is equal to 1.191 kilowatt. What is the torque? Opposing torque is equal to, that is force into d by 2, and power you can also write as power is equal to torque into omega, that is equal to F.
So what is pressure exerted by a fluid? See, pressure is defined as the normal force exerted by a fluid per unit area. See, in this figure you can see there is a 60 kilogram man exerts a pressure of 0.6 into 10 raised to 4 Newton per meter square. You can see this pressure, and on the right side you can see that it is a 120 kilogram man. The pressure exerted by the ground on his body is 1.2 into 10 raised to 4. So the pressure is defined as force divided by area, the area at which the force is acting. So what are the units of pressure? So commonly used units of pressure are Pascal, bar, and Newton per meter square. The SI unit is Newton per meter square, and 1 Pascal is equal to 1 Newton per meter square. And another commonly used unit is bar. So 1 bar is equal to 10 raised to 5 Pascal, and 1 atmosphere is equal to 1.01325 bar, or in other terms it is 1.01325 into 10 raised to 5 Newton per meter square. So atmospheric pressure normally will be equal to 1 bar. So what is gauge pressure and vacuum pressure? The actual pressure at a given position is called the absolute pressure, and it is measured related to the absolute vacuum. So that means at this point it will be zero pressure. But most pressure measuring devices, however, are calibrated to read zero in the atmosphere. And so they indicate the difference between absolute pressure and the local atmospheric pressure. The difference is called the gauge pressure. Pressures below atmospheric pressure are called vacuum pressures and are measured by vacuum gauges. The vacuum gauges indicate the pressure difference between the atmospheric pressure and the absolute pressure. So this is the gauge pressure. This is the pressure measured above the atmosphere. So absolute pressure will be at this point will be equal to gauge pressure plus atmospheric pressure. See, absolute gauge and vacuum pressures are all positive quantities and are related to each other by the following equations. So the equations are, that means P gauge is equal to P absolute minus P atmosphere. You can see that here. This is the absolute pressure and this is the gauge pressure. So P absolute minus P gauge will give you the atmospheric pressure. And P vacuum is equal to P atmosphere minus P absolute. So at this point, if you take this point, the absolute pressure is P absolute here and atmospheric pressure is P atmosphere. So you can see that P atmosphere minus P absolute will give you the vacuum pressure. Okay, this is how the absolute pressure, vacuum pressures and atmospheric pressures are related to each other.
So what is Pascal's law? The Pascal's law states that the external static pressure applied on a confined liquid is distributed or transmitted evenly throughout the liquid in all directions. So that is, any change in pressure felt in any part of a confined incompressible fluid will be felt in all other parts. So take the case of a toothpaste. The toothpaste, when you press here, there's a change in pressure. So this same change in pressure is also felt here, which causes the paste to come out. So that is called Pascal's law. So in other words, you can say that the pressure acting on a fluid is equal in all directions. So let us go to the proof here. So for proving Pascal's law, so we are taking a wedge-shaped fluid element. That means if you take a fluid here, so we will take a wedge-shaped fluid element which is of infinitesimally small dimensions. So, so the dimensions are delta x, delta y, and delta z. And the depth of this fluid element is 1, taken as unity. That means the depth, if you take the direction perpendicular to this paper, so in that direction its length is 1. So what all are the various forces acting on this fluid element? So if you take in the y direction, you can see that there is a pressure P2, and in the x direction you have a pressure P1, and this direction you have a pressure P3 that is perpendicular to the plane. So if you take the x direction, so what all are the forces acting in this direction? And similarly, if you are taking the y direction, what all are the forces acting on this direction? Since the fluid element is stable, that is in equilibrium, that means all the forces are balanced. So all the forces in the x direction and y direction are balanced. So let us write the forces in the x direction. So x direction, the forces acting is equal to the pressure here into the surface area here. So the surface area here is delta y into 1, that is the length, vertical length, into the depth, that is unity. So that is equal to P1 into delta y into 1. And for the, what is the force in this direction? F is equal to P3 into delta Z into 1. 1 means the depth, that is unity, we have taken it as unity, into 1. And if you resolve this force, so this force is in this direction, if you resolve this force, so this is Fx and this is Fy. So Fx will be equal to P3 into delta Z into 1 into sine theta. And Fy will be equal to P3 into delta Z into 1 into cos theta. So, and sine theta is equal to delta y by delta Z, that is trigonometry. So we can write P1 into delta y is equal to P3 into delta Z into delta y by delta Z. So that means delta Z will be cancelled off and here delta y will be cancelled off. That means P1 is equal to P3. So here it is P3. Not P2, it is P3. P1 is equal to P3. Now we want to prove P2 is equal to P3. For that we will take the y direction. So what all are the forces acting in the y direction? So if you write, you can see that there is a force acting here, that is P2 into delta x into 1, just like the earlier case. So P2 is the pressure and delta x into 1 is the area. This will be equal to P3 into delta Z into 1 into cos theta. We have seen how the forces are resolved. We resolve the forces to find the Fy. Fy is equal to P3 into delta Z into 1 into cos theta. And you know cos theta is equal to delta x by delta Z. That is basic trigonometry. And if you substitute cos theta here, you will get this is P2, P2 and this is P3. This is P3. So P2 into delta x will be equal to P3 into delta Z into delta x by delta Z. So delta Z will be cancelled off and delta x will be cancelled off. That means you will get P2 is equal to P3. So that is how you prove, that is P1 is equal to P2 is equal to P3. That means pressure will be equal in all directions. So this is another application of Pascal's law. You can see that the pressure is transmitted equally in all directions. So when you apply a force here, a pressure is created here. That pressure will be transmitted at this point also. So any pressure change that is felt in any part of that confined incompressible fluid, that pressure will be felt somewhere else or in all other places. So whatever pressure that is applied here, you will get the same pressure here also. So this is a small video that is showing that. So you are applying a pressure, so that pressure is transmitted equally in all directions. So, so that means P is equal to F1 by A1. This will be equal to F2 by A2. So this is the principle used in hydraulic jackets. That means by applying a small force here, you can lift a heavy load here. Because F2 will be equal to, F2 is equal to F1 into A2 by A1. So since A2 is greater than A1, very much greater than A1, you can get a very large force there. So that means you can lift a very heavy load.
So what is a barometer and how will you measure the atmospheric pressure? You can see that this is a vessel in which mercury is filled and this is exposed to atmosphere, and this position is B. We have seen that this is the B here, is the position. So what will be this height of this liquid column? If there is vacuum here, there is vacuum, what will be the height of this liquid column? How will you find? To find out, you can consider 2 points, point B and this location. You can see that this is a connected fluid system and both are at the same level. That means pressure at B should be equal to P atmospheric pressure. So PB is equal to P atmosphere. We are making use of this principle. But what is the pressure at B? This pressure is due to the hydrostatic pressure of this liquid column. And here it is vacuum. Since it is vacuum, there is no pressure here. So the pressure is solely due to the hydrostatic pressure of this liquid column. So PB is equal to rho GH. So P atmosphere will be equal to rho GH. In that way you can find out H, that is P atmosphere by rho G. Right? So P atmosphere is equal to 1.01 into 10 raised to 5, the atmospheric pressure. Rho, if it is mercury, it is 13,600 into 9.81. This is equal to 760 millimeter. So in a way you can say that 760 millimeter of mercury column is equal to atmospheric pressure. And what will be the case if this is water instead of mercury? If it is water, then Here this rho needs to be changed. So 13,600 will be changed to 1000. So you will get 10.3 meters of water. So in a way you can see that 10.3 meter hydrostatic pressure due to the 10.3 meter of water is equal to atmospheric pressure. So that is the application of barometer.
In this lecture, we will do a problem on pressure. So the problem is a vacuum gauge is connected to a tank. And it reads 30 Pascal. So it reads 30 Pascal. So the vacuum pressure is 30 Pascal. And the atmospheric pressure, that is barometer reading, atmospheric pressure is 755 millimeter mercury. You need to find the absolute pressure in the tank. So you know that this is the atmospheric pressure. This is the absolute pressure, and this is the pressure you are measuring, that is the vacuum pressure. Vacuum pressure measures the pressure below the atmosphere. So you need to calculate the absolute pressure. So atmospheric pressure is given as 755 millimeter mercury, and this is given as 30 Pascal. So both are given in different units. So let us see what is atmospheric pressure in Pascal. That is equal to 755 millimeter mercury. That means the formula for calculating the pressure in Pascal is rho gh. So rho is the mercury here. So 13,590 into 9.81 into 755 millimeter. So that is given by 10655.01455. So absolute pressure will be equal to P atmosphere minus 30, that is equal to 10625.01 Newton per meter square. So this is how you calculate the absolute pressure.
What is a manometer? Manometer is a device used to measure the pressure of a fluid. So you can see here in this figure, this is an inverted U-tube manometer connected to a vessel. So this is the vessel here. You can see the pressure here is changing continuously. It is changing from atmospheric pressure to vacuum pressure, and then to gauge pressure, and then to atmospheric pressure. You can see that when there is vacuum pressure, the liquid in the left column rises up, and when there is gauge pressure, liquid in the right column rises up, and in the atmospheric pressure you can see the liquid column on both limbs will be same. So this variation in height, by measuring this height h, you can measure the pressure inside this vessel. So this formula is used to measure the pressure. So if you can measure h, then you can find out the pressure. So how will you measure the pressure? See, here you can see a inverted U-tube manometer, and on the left side you need to measure the pressure. Here this is the pressure you need to measure. You can see that at position 1, so here this is a pressure P which needs to be measured. And at position 2, you can see that if you draw a horizontal line at this interface, that is 1, 2, this is a liquid here, this is a liquid. So at a horizontal level, the pressure acting on the fluid will be same at these 2 points because the height is same. We have seen that in hydrostatic pressure. So in hydrostatic pressure, you can see that when you draw a horizontal line, the pressure at all the points will be same. It depends only on the height. So we are making use of the principle that is in the line 1, 2, the pressure will be same. So what will be the pressure acting at 2, that is P2? And what is the pressure acting at P1? Both will be equal, that is P1 will be equal to P2. So you can see that on the right side, P2 will be equal to, so this pressure will be equal to, on the top you have atmospheric pressure acting, and there is a pressure due to hydrostatic pressure due to this liquid column is also acting here at this point. So P2 will be equal to P atmosphere plus rho GH. And what will be P1? P1 will be equal to P, this pressure, because there is no liquid here. So it is, since there is no liquid here, so this P will be equal to the pressure here. So P1 is equal to P. So if we equate these two, you will get this equation. So let us see an application of a U2 manometer for measuring the pressure difference between pressure in a fluid flow. So you can see that this is the inverted U2 manometer here. This is the inverted U2 manometer. You can see that there is a small change in shape here. It is inclined here. There is a slight inclination there. And how will you measure the pressure? You need to find the pressure difference between 1 and 2. That is P1 minus P2. For this, I told you we will first find the interface. Lowest interface. So here there is an interface between two liquid. So here there is a liquid with a density ρ2, and here inside there is a liquid with ρ1. This is also ρ1. So we will find an interface between the two liquid and the lowest interface. So this is the lowest interface. So then we will find out the pressure acting here and also the pressure acting here. Both will be equal. We have seen that because the liquid is at the same height. So the pressure at both this position will be same. So that PA is equal to P1 plus ρ1 G into A plus H. This is the hydrostatic pressure, and this is the fluid pressure acting here, and the hydrostatic pressure is solely due to the height only. See, there is no effect of this inclination here, only the height is considered. This height is equal to A plus H. So ρ1 G into A plus H. And what is PB? PB is equal to P2 plus ρ1 G into A plus ρ2 G into H. See, P2 is the pressure here. This is the pressure here, P2. And there is a liquid column here. This exerts a pressure that is equal to ρ1 G into A. And here also there is a pressure that is equal to ρ2 G into H. So together this is the hydrostatic pressure. Since both are equal, PA is equal to PB. Both are equal, PA is equal to PB. So you can write P1 plus ρ1 G into A plus H is equal to P2 plus ρ1 G A plus ρ2 G into H. So P1 minus P2 will be equal to ρ1 minus ρ2 into G into H. This is how you calculate the pressure difference. in a pipe using a U-tube manometer. Remember that there is no effect of inclination in the values. In this lecture, we will do a problem on U-tube manometer. So the problem is like this. The right limb of a simple U-tube manometer containing mercury is open to the atmosphere, while the left limb is connected to a pipe in which a fluid of specific gravity 0.9 is flowing. The center of the pipe is 12 cm below the level of mercury in the right limb. Find the pressure of the fluid in the pipe if the difference of mercury level in the two limbs is 20 cm. So let us try to draw this. So this is the pipe. So this is the pipe inside which fluid is flowing, that is of specific gravity 0.9, and the center of the pipe is 12 centimeter. So this side of the U-tube manometer is open to atmosphere. Okay, this is the level of mercury, and the center of the pipe is 12 centimeter below the level of mercury, and the difference of mercury level in the two limbs is 20 centimeter. Okay, so let this be the interface, and this height is 20 centimeter. This height is 20 centimeter. So here another fluid is flowing, and this is mercury of specific gravity 13.6. Okay, this is the schematic of the problem. Now let us approach this problem. So in order to find this, we will draw an interface. So this is the interface, so 1 and 2. So when we draw the interface, make sure that when you draw this line should be at the interface, at the lowest interface. So here we have another liquid, that means specific gravity of 0.9. So let us try to draw this line. And at this point, since the liquid is at the same level and this is a connected liquid, the pressure at P2 and P1 will be equal. That means P1 will be equal to P2. This is the same liquid and this is the same level. So P1 is equal to P2. Now let us find what is P2. So P2 is equal to, on the top you have atmospheric pressure, that is equal to P atmosphere plus rho Hg into 0.2 into G, and see P1 is equal to, so this pressure, let us take it to be P plus the hydrostatic pressure here, and this height is equal to, if you see this height will be equal to 8 centimeter. So rho of fluid into 0.8, sorry, it is 0.08 into G. The formula is rho GH, or you can write rho Hg. So this is rho gh, 0.08 is h, g is the acceleration due to gravity. And if you equate these two, you will get p plus rho f into 0.08 into g is equal to p atmosphere plus rho hg into 0.2 into g. So p is equal to p atmosphere plus 13600 into 0.2 into g minus rho f is 900 into 0.08 into g. So this is equal to, that is p atmosphere plus 25,976.88 Pascal. So if you are taking only the gauge pressure, you can remove p atmosphere. So p you can say it to be 25.97 kilopascal, or you can say 25.98 kilopascal. So this is the gauge pressure. That means the pressure above the atmosphere. What is fluid statics? Fluid statics is the study of incompressible fluids at rest. Let us first see what is the hydrostatic force on a submerged vertical plane surface. For this, consider a liquid in a beaker here. And let us take a vertical submerged body. So this is an arbitrary body. So what is the force acting on this plane surface? This surface is kept vertical to the liquid. For this, we will consider a small elemental area of this plane surface, that is dA, which is a height of h. So the pressure acting at this small area is rho gh, that is the hydrostatic pressure. And the small elemental force acting on the plane surface is equal to pressure into dA, which is equal to rho gh into dA. So the total force acting on the body is equal to integral of dF. And that force is equal to rho gh dA, because dF is equal to rho gh dA. So if you take integrated, you will get rho g integral h dA. And integral h dA is equal to A into h bar. So this is how you find the centroid of the body. H bar is the centroid of the body. So the total force acting on the plane surface is equal to rho g A into h bar, where h bar is the distance of the centroid of the body from the free surface. So this is h bar. So the total force is equal to rho g into A. A is the total area of the plane surface. H bar is the distance of the centroid of the body from, so this is h bar will be somewhere here. This is h bar. So g is the centroid of the body and h bar is the distance of the centroid from the free surface. So how will you find the center of pressure of the same plane surface? So if you take the plane vertical surface here and the centroid be at G, the center of pressure will be slightly lower than the centroid of the body, because in the upper portion the pressure will be lower and the bottom portion the pressure will be higher than the upper portion, because as you go down, hydrostatic pressure increases. So the lower portion of the body experiences a slightly higher pressure than the upper portion. So the center of pressure naturally shifts downward. So how will you calculate the center of pressure of this plane surface? So you can see this h bar is the distance of the centroid of the body from the free surface, and h star is the distance of the center of pressure from the free surface of the liquid. So in order to find the center of pressure, we will consider a small elemental area dA, which is at a distance of h from the free surface. So the total force dF is equal to elemental force dF is equal to P into dA, where P is equal to rho g, as we have seen that earlier, and dA is the elemental area. So what will be the moment, that is dm, due to this small elemental force about this line, about the free surface? So the dF, the elemental force, is acting perpendicular to this surface. So this causes a moment dm, and this moment is equal to dF into h. So the total moment is equal to integral of dm, that is equal to rho gh dA into h, because moment is equal to force into perpendicular distance, and total moment will be equal to rho g integral dA h square. But integral dA h square is defined as the area moment of inertia of the body, that is integral dA into h square. So you can replace m is equal to rho g into I0. So according to the principle of moments, we have calculated the total moment by integrating the elemental moment. So according to principle of moments, total moment can also be written as total force into h star, where h star is the distance of the center of pressure from the free surface. So F is equal to rho g A into h bar, we have derived in the last class. So F into h star is equal to rho g into I0. So h star will become rho g I0 by AH bar. So this is the formula for the center of pressure. So according to the principle of parallel axis, I0 is equal to Ig plus AH bar square, where Ig is the area moment of inertia about the centroid, and A into h bar square is equal to area into the centroid, distance of the centroid from the axis, the free surface here. So I0 is the moment of inertia about the area moment of inertia about the free surface, Ig is the area moment of inertia about the centroid, plus A into h bar square.
So in this problem, we will do a problem on center of pressure and hydrostatic force. So here the problem is given as a vertical rectangular gate of 4-meter width and 2-meter depth is hinged at a point 0.25 meter below the center of gravity of the gate. if the top edge of the gate is 5 meter below the free surface of the liquid. So first we will draw the gate. So here a gate is attached here. You can see the gate here. So the top edge of the gate is at a height of 5 meter. The total depth of the water is 7 meter. So if you draw the view of the gate here, side view, it will be like this. It is given the height is 2 meter deep. This is 2 meter deep and is 4 meter wide. This is 4 meter wide. And the gate is hinged at a point here, that is at a height of 0.25 meter. It is 0.25 meter here. So first we will find. So the question is to find the horizontal force that must be applied at the bottom to keep the gate closed. So you need to apply a force here, that is F. That should keep the gate closed because it is hinged about here. It may open about this hinge. So you need to apply a force to close the door, close the gate. So first we will find the centroid h bar, that is distance of the centroid of the gate from the free surface, that is equal to 5 plus 1. This is the distance of the centroid, that is the center of the gate from the free surface, that is equal to 6 meter. So the force is given by the formula rho Ga into h bar, that is equal to 1000 into 9.81 into this area of the gate is 4 into 2 into h bar is equal to 6. That is equal to 470,880 Newton. So at what point it is acting? It will act at the center of pressure, H star. So H star is given by the formula Ig by AH bar plus H bar. That is equal to, for a rectangular gate, this will be BD cube by 12 into B into D into 6 meter plus 6. That is equal to D square by 12 into 6 plus 6. That is equal to 6 plus 1 by 18 meter. That is equal to 6.055 meter. So it will act somewhere here. So the force will be acting here, F. So this is the distance of the center of pressure, H star. So center of pressure is 6.055 meter below the free surface. Now this will cause a couple about this hinge. So you can call this hydrostatic force F, and this force is the opposing force that you need to apply. So the couple created, the moment that is created at the centroid, at the Hint is Fh into this distance. This is equal to 0.25 minus 0.055. So this couple will cause the gate to open. This will be countered, this need to be countered by the opposite force, that is F into 2.25, that is this distance, 2.25. So you can calculate F, that is equal to 470880 divided by 2.25 into 195. This is equal to 4809.6 Newton. Or you can write it as 40.8 kilonewton.
Now we are moving to buoyancy and Archimedes principle. See, what is Archimedes principle? Archimedes principle states that when a body is immersed in a liquid, it will experience an upward force that is called the buoyant force, which is equal to the weight of the displaced water. In this GIF, you can see that the weight is slowly lowered downward. The weight initially weighs around 11 pounds. When it is dipped into the water, you can see that the final weight becomes 4 pounds. That means a total loss of 3 pounds. You can see that what is the weight of the fluid displaced? It is 3 pounds of water. So here you can see that when the weight is dipped, the weight measured is reduced to 4 pound. That means a 3 pound weight is acting upward, which is the buoyant force. The weight is reduced because of the buoyant force. There is gravitational force and there is an upward buoyant force which is equal to the weight of the fluid displaced. That is 3 pound of water. So this is the concept of buoyancy, and Archimedes principle is used to find the buoyant force. Then what is center of buoyancy? See, center of gravity means there is the center of the body. That means the weight of the body is acting. So here it is point G. The weight of the body is acting at this point. This body is partially submerged in water. So total about height h is submerged. So center of buoyancy is the center of the displaced fluid. So that means at water up to a height of h is displaced. So what is the center of that displaced fluid? That is the center of buoyancy. At this point, buoyant force is acting. So gravitational force is acting at the center of gravity, and buoyant at point center of buoyancy, the buoyant force is acting.
In this lecture, we will see what is a metacenter. You can see here a vessel. In vessel's center of buoyancy is B. It is floating. Center of gravity is here G. You need to find the metacenter. When this vessel is tilted, the center of buoyancy will be shifted rightward, and a force will be acting through this center of buoyancy, through this new center of buoyancy upward, and center of gravity will remain same. Center of buoyancy will be shifted rightward. So if you draw a line through here, it will meet the earlier vertical axis at a point, and this is called metacenter. So metacenter is defined as a point about which the imaginary axis drawn through the new center of buoyancy will meet the vertical line passing through center of gravity and old center of buoyancy. And here the metacentric height is gm. Now how will you find the metacentric height? See, metacentric height is found using the formula I by V minus Bg. See, I is the area moment of inertia, and V is the volume of fluid displaced, and Bg is the distance between center of gravity and center of pressure. So if you take a fluid like this, and this is your body. So if you draw the top view of this body, it will be something like this. The view from the top. Okay. So in order to calculate the metacenter, or metacentric height, that is gm. Here. This is the new center of buoyancy B dash. This is m. So this is gm, that is distance between center of gravity and metacenter. So gm is equal to I by V minus Bg. So here it is B. This is center of buoyancy. Bg is the distance between center of buoyancy and center of gravity, and volume is the amount of water displaced, that is volume of fluid displaced. So that is this much volume, and I is the area moment of inertia about this axis when you view from the top. So here this height may be h and width is b, so this will be b. And the top view, you can see that this may be the L, that is length of this body, that is the top view. So here area moment of inertia is equal to LB cube by 12, because you are finding the area moment of inertia about this axis, that is LB cube by 12. So this is how you calculate the metacentric height.
In this lecture, we will do a problem on metacentric height. There's a problem to find the metacentric height. So the question is, a solid cylinder of diameter 5 meter has a height of 4 meter. Find the metacentric height of the cylinder when it is floating in water with its axis vertical. And the specific gravity of the cylinder is given as 0.6. So let us draw the figure. So you have the cylinder here, and it has got a diameter of 5 meter
and a height of 4 meter. You don't know how much it is submerged or how much it is floating. So let us take it as h. That is a portion, length of the portion below the water. So first you need to find h. So for that, first we will find the density of the cylinder. That is 0.6 into 1000. Because specific gravity is given as 0.6, so that is 600 kilogram per meter cube. Since the body is floating, according to Archimedes principle, the weight of the body, weight of the cylinder is equal to weight of the fluid displaced. Okay, so weight of the cylinder is rho into the total volume into G, and weight of the fluid displaced is rho of water into volume of the fluid displaced into G. So what is the total volume? That is, this is 600. The total volume is say it has got a diameter of 5 meters, so cross sectional area pi by 4 into 5 square into 4 into G, that is equal to rho of water is 1000 into the volume of water displaced is pi by 4 into 5 square into H into G. So you can cancel it off. So that means H is equal to 600 by 1000 into 4. So that means it will come out to be 2.4 meter. So H is equal to 2.4 meter. Now, what is metacentric height? GM. The formula for metacentric height is I by V minus BG. See, center of buoyancy will be here, that is it is a height of see, the total height is 2.4 meter, so this will be 1.2 meter center of buoyancy, and center of gravity will be here. That is at a position of 2 meter. That means total length is 4, so it is up to, it is 2 meter. That is 2 meter. Now that means BG will be equal to 2 minus 1.2, that is equal to 0.8 meter. And what is I? See, I here is, see, on the top view you can see that this is a cylinder, so you need to find the moment of inertia of the top area about this axis. So I here will be equal to, I here is equal to pi by 64 d raised to 4 is the moment of inertia of the top view. So this is equal to, and the volume displaced is equal to, right, so I is equal to pi by 64 d raised to 4, and volume displaced is equal to, you know the formula, pi by 4 d square into h minus bg is 0.8.
So that is equal to d square by 16 into h minus 0.8. So and d square is 16. So it is 16 divided by 16 into h is 2.4 minus 0.8, and this is equal to, you will get it as minus 0.38 meter. See, you are getting a negative value for metacentric height. So metacentric height is equal to minus 0.38, which is less than 0. That means metacentry is below the center of gravity and the body is unstable. That is what you can infer from this value. In this lecture, we will discuss about the stability of a partially submerged body. So you can see here this body. So this is floating here, and you can see the center of buoyancy here and center of gravity is here. That means center of buoyancy is just below the center of gravity. At the center of gravity, weight of the body is acting downward. At the center of buoyancy, the buoyancy force is acting upward. And this body is given a slight tilt. So what happens then? So you can see this vertical axis passing through the earlier buoyancy point and gravitational center of gravity. Now when it is given a tilt, the center of buoyancy will shift towards right because more fluid is displaced in the right portion. So this is B1. And if you draw a vertical line through this point, that is a buoyant force, the vertical line showing the buoyant force, it will intersect the earlier line at this point, and this is called the metacenter, as we have discussed earlier. Now, see, now the weight of the body is acting to the center of gravity and the buoyant force is acting through the center of buoyancy. These two forces, you can see that it is not, it is a distance apart. This causes a moment. So that means it will be like this. This will cause a moment that is the anti-clockwise direction. So because of this moment, this body will come to its initial position, and that is called a stability. Stability means when the body is given a tilt, it should come back to its initial position. So because since this is the moment created, that is anti-clockwise moment is created, it will come back to its initial position. Similarly, when the body is given a leftward shift, when it is tilted to the left side, a clockwise moment will be created, which causes the body to come back to its initial position. So that is why it is called the body is stable. That is why the body is stable, and this is called stable equilibrium condition. And let us see an unstable equilibrium condition. So you can see the body. So the center of gravity here, center of gravity is little upward, and center of buoyancy is here. So in this case, when it is given a tilt, the new center of buoyancy is B1, and the metacenter will be here. The metacenter will be here. So just look at the forces. The buoyant force is acting at B1, and gravitational force is acting at G. So let us see the couple that is created. You can see that the couple created is in the clockwise direction, and this clockwise moment will cause the body to tilt rightward. It will not come back to its initial position, initial stable position. So this body is said to be unstable. So this condition is the unstable equilibrium condition. For the stability of the partially submerged body, the condition is metacentric height should be greater than 0. So in the earlier case, you can see that Gm, that is positive. In this case, the metacenter is below the center of gravity. So that means in this case, Gm is less than 0. So the body is unstable. In this case, Gm is greater than 0. So the body is stable. So this is the condition for the stability of a partially submerged body. Now let us see the stability of a fully submerged body. What is the condition for the stability? You can see here in the left side the figure. So the center of gravity is here and the center of buoyancy is here. So the weight is acting downward at the center of gravity, that is W, and at B the buoyant force is acting upward at B. And just like the earlier case, we are giving a tilt to this body. So when it is given a tilt, the center of gravity will remain here and center of buoyancy will be shifted towards rightward. A little center of buoyancy will be somewhere here. So if you draw the forces FB and W, so the forces will be like this, FB and W. This will cause a couple which will tilt the body back to its initial position. That is, it is creating an anti-clockwise moment. So this is called a stable equilibrium. That means the body is coming back to its initial position. So the body is stable. If the body is given a tilt towards right, it will come back to its initial position. Similarly, if the body is given a tilt towards left, it will come back to its initial position. So the condition is the center of buoyancy should be above center of gravity for a fully submerged body to remain stable. Let us take an unstable equilibrium condition. Here the center of buoyancy is below the center of gravity. So the weight is acting downward at center of gravity and buoyant force is acting upward at the center of buoyancy. So when it is given a tilt towards right, you can see that there is not much change in the position. So when it is given a tilt, the center of buoyancy will be acting here and center of weight is acting downward here. So this will cause, you can see that this force will create a clockwise moment, which will further cause the body to tilt rightward. It will not come back. That means the body is unstable. For a body to be stable, it should come back to its initial position. So you can see that the condition for stability is center of buoyancy should be above center of gravity. Now let us take the case of a neutral equilibrium. In neutral equilibrium, you can see that both center of gravity and center of buoyancy are at the same point. That means there is no couple created here. So it is said to be a neutral equilibrium. So we see that for a stability of a fully submerged body, center of buoyancy should be above center of gravity. So this is the condition for a full stability of a fully submerged body.